Okay, so I hope everything is still working after a week not doing anything here. So, hi everyone. Yeah, last week I was pretty much sick the whole week. My voice was entirely gone, so there was absolutely no chance that I could do a single stream. Talking for more than 4 or 5 minutes was just almost impossible. Yeah. So I hope we can all stick back to the regular schedule. I had a week of buffer in the original plan. That is now gone. Yeah. I don't know how long my voice will keep up today. It's much better than last week, but I'm not entirely sure how good it really is at the moment. So let's see how long it lasts. What are we going to do today? Last time we started building some of our some editors for our programming language, mostly manual, and had a single or a brief introduction into grammar cells and how it's useful for editor definitions and deriving behavior of them from the definition itself, without requiring us to specify it in a separate language aspect as MPS would usually require it. Okay. And today we will continue on that. We had a brief introduction last time, and today I'm trying to go a bit deeper there and show some of the more advanced features that make it quite easy to get a usable expression language. Okay. So let's recap what we built last time. We have our little toy language here. It allows us to define variables. And then the variables can have initializers. We also have some basic support for nicely entering expressions here. So we can type 1 plus 2 plus 4, something like this. Yeah, wait. Sure. Let me change the scene. Sorry for that. This should be better now. Okay, so let's start from scratch. So you can define variables here. Variables can have names. There's currently no checking going on if there are duplicate names or things like that. We will come to that later. You can initialize variables with various kinds of expressions. But currently those expressions, the only expression you can enter nicely is the plus. If I type something else, like 1 times something, it doesn't work because we had to define what happens if you type plus on a number literal manually, and we have only defined it for plus, not for anything else. And we can also only do it on the right side. So on the left, it doesn't work. So if you type plus left of a number, nothing happens. The editor just gets red. Okay. So let's change that. The code responsible for handling the plus is this one. So it's this thing the MPS calls a side transformation. And this one is only defined for the right side. So let's see if we can use grammar cells, which is a DSL for defining editor definitions, to get rid of this. So let me first delete this. Okay. And now let's go to our binary expression. So the plus is a binary expression similar to the minus and the multiplication expression. So our binary expression has a left and a right side. And then in the middle, we show the alias, which in our case is here, plus for plus, and the star for multiplication, etc. And let's go back to the binary expression here. So we already generalized this last time by putting the alias here instead of having individual editors for all of the different binary expressions. We created a generic one and reused the alias. But in order to derive the more behavior from the editor definition, so how should it feel to the user, in our case more text editor like, we have to use grammar cells. And all the grammar cells concepts are basically prefixed with grammar dot, and then it's the various kinds of editor definition concepts that you can see here. And what we need to do is we want to make our language behave more text-like. And to do this, grammar cells allows us to involve parsing at some of the locations in the editor to make it easier for the user to enter text. While MPS in general is a projectional editor, so there's no parsing going on. In some cases, we want to at least involve some parsing for the input that the user has entered. And to do this, we can use this grammar rule cell. And when we select this, we can immediately see two things in the editor. So one is it allows us to define a projection, which is similar to, which simply allows us to define a normal MPS editor here. And then there's grammar, which in our case, we now derive from the projection, but it also allows us to customize things later on. Like for instance, the associativity or the priority of an expression, and we will come to that later, why this is useful. So let's first take a look at how the editor definition should look like for our binary expression. So first of all, we need a horizontal collection again, which allows us to show things in a single line in MPS. This wraps everything. And now what we want to do is on the left side, we want to show the left like this, but now comes something you need to know. And that is that in our case, we want to be able to wrap it, right? So the user should be able to type the left part and then add the plus or the right part and also add the plus on both sides. And to get this, we have to give some hints to grammar cells here, and that is done with the wrap cell. So we have used this last time already. They're in a different context. So there the wrap cell was used that you can enter an expression at the point where we were expecting an expression statement. Here we are doing something similar. So for the left side, we want to have it wrappable. The middle, I leave it open for now because we have to do something else there. And for the right side, we also want to wrap. Wrap. And then the right. Okay. And in the middle, we want to show the alias. But we need to make grammar cells aware of the fact that this is a constant in the grammar. So this is something MPS should handle, or grammar cells, when it parses the input from the user, should handle as a constant, and therefore there is a specific grammar cells concept here as well, and that is called grammar constant. Okay. When we add this to the language, we get immediately an error here in the editor definition, and that is because in the inspector down here, we need to return the value here. Of course, we could just so we could just return the static plus, but last time we already had some more dynamic behavior that we show the alias. So what we want to use in the middle between the left and the right side is again the alias. And instead of just using the usual editor component that we used last time, which is this one, so this alias thing, then we get a warning here that it will be inlined, which we don't care at the moment about. We also don't want to use this because we really want to tell grammar cells that in the middle of the two, in the middle between the two parts of the binary expression, it expects a constant. So constant again, and now instead of returning like a fixed string, what we get here is the concept that we are currently operating on. So this is then, since our binary expression is abstract here, it's all subconcepts of the binary expression. This is why in the function signature here, you can see subconcept as a parameter that you get in here. And if you check its type, we can see that it is a concept of type binary expression that we get here. And we want to return the alias. So let's select concept alias here. So all the on the concept definition that we operate here, we can always get the alias that was defined in the structure aspect, and we do the same here. So just by accessing the alias operator, the alias operation here on the subconcept that we get. So let's build the language and see what happened now. So okay, no, I don't want to move anything. Let's go back to our workbook. Define a new variable x, type 1, and now we type plus 2. That works as before, even if we deleted the old definition of it. But what also works is we can now type it on the left side, and it also works. So from the definition of our editor, grammar cells have now derived how transformations should happen. Usually this is enough that you need. So it now also works for all the subconcepts. So we have the multiplication expression here, the mul expression, and it has the alias star or asterisk. And if we go now here and we type it, we get automatically a transformation for this. And it also works for the minus expression. So if we type minus, it also works. So we get it basically for free for all the subconcepts because our definition of the editor stats, this is the general rule. It has some dynamic behavior in it. So for all subconcepts that exist, these actions are derived. And to add a new binary expression now to the whole system here, we can just create a new concept. Diff expression, for instance. We don't have one yet. Yes. It extends binary expression. And now the only thing we do is we set the alias. We build our language. And now let's go back to the workbook. And it works. So this way it's really easy to get consistent editor behavior for all the subconcepts of a given concept. But there's still something missing, so let's do something here. I mean, it still works as before in the sense of that you can type the plus first and then get both operands, just like you would usually get when you don't do anything in MPS. But if we now have like plus multiplied by 10, no, let's do this. So we have 10 times 10 plus 10. Okay. What should happen in this case? Let's take a look at the Node Explorer here. So the Node Explorer shows us the underlying AST here. And if we open it, take a look at the structure. What we can see is that there's a plus expression on the top of the AST. So directly under the initializer of the variable x in this case, we have a plus expression. And on the left side of the plus expression, there is the multiplication expression. And on the right side, there's a number literal. But this is not correct. So the AST is not shaped in the way we would like to evaluate it, because the multiplication has a higher priority than the addition, than the add expression at the end. So if we would evaluate the AST, the multiplication needs to happen first before we add 10 to the result of the multiplication. And if we would now evaluate the AST in the order that it's at the moment, we would first run the plus. So 10 plus 10, which is 20. And then we would multiply it by 10, which would lead us to 200, sorry. Which is not correct, because what should happen is that we first do 10 times 10. Yes, you are correct, right. This time it's balanced, yeah. Sorry for the confusion. Let me enter it the other way, then it gets clear. Sorry. So if we first add the plus and then the multiplication, I think. So let's do 10 plus 10 times 10. And we now take a look at the, yeah, okay. Thanks for the pointer. So, yeah, in this case, no, it's wrong. So if we now evaluate the AST, we would first encounter the multiplication, then walk down to the left side, which has the plus. So we would encounter the plus here with two number literals, in this case 10 plus 10. They would be added together with this, which is 20. And then when we go up again, we would encounter the right side, which is another number literal of the multiplication here. And then we would multiply the 20 by 10. But what we would like to do is we first want to multiply 10 by 10 and then add 10 to it. So to do this, we need to somehow tell the editor that there's priorities going on between these various kinds of expressions, and that the multiplication has a higher precedence than the add operation. So to do this, we need to do two things. So let's go to the binary expression first. If we take a look at the editor definition here, there is the projection part that we edited first, which describes how it should look on the editor and how it also should behave. But then there's also the rules part down here. And if we take a look at the inspector of it, what we can see here is that we can first of all decide if the expression that we encounter is left associative or not, and the priority of the expression or of the sub-concept of our binary expression here. And how can we do this? The easiest way is to define behavior methods on the concept. So MPS supports two kinds of behavior methods. One that is defined on the instance of a concept, which is the normal one that you would also know from Java. So it's a normal instance method that you get when you create a new behavior method here. So whatever, a Boolean. Let's see. Space. And then we could return true or false here. But what we want to do is we want to have this on the actual concept. So we can make this static. But we also want to be able to override it. So we can make it static virtual. So now subconcepts of the binary expression can override this method. So there are two layers of, or there's another meta level behind the concept instances, which is the concept definition. And the problem is the analogy to Java breaks a bit because static methods on classes, you couldn't really override them. In MPS, you can override static methods on the concept definition. Okay. And the second thing we need, so we go to the editor again. So the first thing we can control now here is if we we get a parameter here that is called subconcept. Subconcept. And now MPS automatically types it to an expression in this case of the concept binary expression, and it gives us access to the methods defined on the concept definition. MPS calls them static concept methods or static behavior methods. So we can access the left associativity here. And we also want to have a priority. So we need to do the same for priority here as well. And I think, if I'm not mistaken, let's take a look. I think priority here is represented as an integer. Yeah, it expects an integer here. So let's add priority method. Make it static as well. And virtual. And now the default implementation, we just return a base value that is the lowest priority in this case, which is 0. And then we can override it when it's needed. So let's go back to the editor and tell MPS that it can access it through the subconcept priority method. If we now build it, the behavior should still be the same as before because all of our expressions have the same precedence or priority. We enter this part, so 10 plus 10 times 10, and we should still get the same AST as before. Yeah. Okay. And now we can override the priority in one of our subconcepts here. So we can go to the multiplication expression. And invoke command O, which shows us what we can override or implement. And we want to override the priority. And let's return 1 here and see what happens. make. Okay, let's delete this part again. 10 plus 10 times 10. And if we now take a look at the resulting AST, we can see that the plus is now on top. So before, let me just disable that for a second here. And just return null. 0 here in this case. And retype the AST. Okay. So in the case where we didn't have any priorities for our expressions, the resulting AST was the multiplication on top and then the nested plus operation. And with the priorities, we can see now that the plus is on top and the multiplication is nested into the plus. So if we now evaluate the AST by just working the AST, we would first encounter the multiplication. We would first encounter the plus, then evaluate its right side, which in this case is the multiplication, which has two operands, the two number literals, 10 and 10, so 10 times 10. So the result of the right side is 100. And then we would go to the left side and encounter the number literal here, which is 10, so it's 100 plus 10. And that's the result we want to get. So behind the scenes, there's some shuffling or resorting of the AST going on based on the priorities. But you don't need to take care of this manually. So when you would implement your transformations with the normal built-in MPS facilities, you would need to invoke the reordering of the AST manually. And in this case, the grammar cells projection, the grammar cells rule takes care of it. So if you have nested instances of these grammar rules, it will pass the complete tree for you and also rebalance it based on the priorities. If you want to get more details on how grammar cells work, there is also a paper written about it, which you can find here, I think. I think it was this one. Nope, not that one. Oh, 1 second. Is it not linked here? Yeah. So let me put it into chat. So you can find it here as well. It describes some of them, also some of the details behind it in the runtime, how certain things work, why we have built this, and also how we ensure that this is still extensible so that you can contribute new rules into the puzzle system with new languages that you define. Okay. The same, I think. So we have now let me order the expressions that we have here a bit more. That it's a bit more clear. Expressions, binary. We have some binary expressions. In our case, the basic abstract binary expression, and then 4 subconcepts at the moment: the minus, the multiplication, the plus, and the division. And so let me just put the expression here. Yes, exactly. It's also I posted the link to it. It's not the one on our original server, but it's on some other university's server, but it's the same paper. Okay. So let me order the statements as well. Variable declarations, also statements. Okay, to just get a bit more order in here. Okay. We also have I forgot to move this. So we actually have 5 expressions at the moment. We also have a equals expression here. Yeah, and let's see if that actually works. Seems to work as well. Yeah, so with the simple editor, or with the single editor definition that we have done for binary expressions here, it's now pretty easy to add new expressions into the language, and they still behave consistent without adding any transformations that you describe manually. In the past, this has really been a pain, so getting all of these transformations right, and not forgetting some at the left or right side of in the whole language that you have. So this is the main reason why we built grammar cells. This is really to get things consistent. I mean, it will not, or for an expression language, it will most probably cover all you need. But if you need to customize it, you can still write your own contributions to the site transformation or substitute menu, and they are still invoked. So it's not replacing what MPS is doing. It's just building on top of it, and it still integrates with everything that is there. So we still have a substitute menu that was okay. This is an empty one. It's a bad example, and I don't have a handwritten one here, but it still works with the normal substitute menu language of MPS, and then all of these substitute actions and site transformations are combined into the runtime of MPS. Okay. So now we can enter some nicer things in our language, so the expressions work better as before, but we still can enter stuff that makes little sense. So we can, for instance, enter 10 plus 10 plus, and then let's select the string literal here, like this. And this is actually something we don't want to allow for the user. We can also do things like duplicating variables. So we now have 2 variables x. They both are defined in the same scope. We might want to allow this. We might not want to allow this. for a start, I would say let's first disallow this. So we should write a rule that somehow we check our workbook if there is any variable with the same name in the same workbook at the moment, so that you cannot redefine a variable with the same name. How can we do this? So this is something that MPS calls a checking rule. High velocity. So checking rules in MPS are part of the type system. They are not used to calculate types, but they are used to check based on the results of the type system. So they have access to the result of the type system. I talked about that in the very early episode about how MPS works in general and what kind of different aspects the language can have. And what we want to do is we want to check if there are variables that have duplicate names. So we need to define a checking rule for that. And wait, let's do this in a different way. MPS doing some more work for us. So on the workbook, we want to have a checking rule. And to add this, we select the type system tab from the aspects of the concept, and then click in the center or to create a new aspect. And in this case, we want to create a checking rule. And then MPS already fills the definition of the checking rule with some defaults here. In this case, it has derived the default name check workbook. It has set the applicable concept to workbook. And now we have a do block where we can actually put our logic. So in our case, what we do is we go to the workbook and then we want to access the content. And now the workbook has different kinds of content. Let's see. So it's statements. And we currently have 3 different kinds of statements. So we have an empty statement, which represents an empty line, an expression statement, and a variable. And in our case, we want to ensure that there are no duplicate variables in the same workbook. So what we do is in the checking, we access the content, and now we want to filter it. So MPS has some language extensions to Java, which allows you to work with instances of the language definition that we have here. And what we want to do is we want to filter out everything that is not a variable. So we want to ensure that we get all the content that is of kind variable. And we want to iterate over it. So for each variable, and now if we access the variable, we can see that it has a name property here. So let's keep track of the names that we already encountered. Let me create a new set case of type string. Var names. So we use a set to keep track of the names that we already encountered. And now we first check if the set already contains the name of the variable that we are currently iterating over. And in case it contains it, we want to show an error. So the type system language has the error statement here. So we can select this, and it takes two parameters. The first one is the actual error message we want to show to the user. Thank you for the follow. So the first thing it takes is the error message we want to show to the user. In this case, we keep it simple and we just say duplicate name, and then we just append the name, the column here is variable dot name, and the point and the second parameter it takes is the model element or the element of the AST where the error should be attached. In this case, it's the variable this. And we definitely want to keep track that we have seen the that we have encountered this name. So we add the variable dot name to the set of names that we have already encountered. So let's build this. And then let's go back to our workbook. And what we see now is that we have a red error squeal here. So MPS behind the scenes executed the checking rule for the workbook and encountered, and our logic basically said check all of the names, and if the set of already visited names contains the name of the variable, then this is an error because the variable name is used twice. And MPS now points out the error message here that we have a duplicate name X in this case. And if we now rename it to Z, for instance, then the error goes away. So MPS also re-evaluates the checking rules based on changes that the user does to the model. Oh, if I know anything about the plans that that JetBrains had years ago to put those editors on the web, I'm not aware of any plans for MPS directly. I know that they had, or that they are working on this other web-based kind of tooling, which is inspired by MPS. So these, I think last year they had this consensus example. Yeah, there was some demos MPS based where they had a dedicated aspect of a language where you can define a web editor for the concepts. I don't think there's anything going on in that direction. There is the JetBrains core. I think they had an example of something that was MPS inspired years. Constance, I was unable to type it, but it's. Don't remember the name. It was based on some other technology, which is, I think, Jetpad, which is developed by JetBrains themselves. They had some web. Was it Python? I don't remember the name, but there was something. Yes. The company that I'm working for, so I'm shameless plugging it now, is also working on something in that direction. Yeah, Datalore, exactly. So yeah, this was the name. Data or JetBrains, exactly. So this is based on Jetpad, which is inspired by the principles behind MPS, but it's not built with MPS as far as I'm aware of. Yeah. But directly in MPS, I think there's no current development going on in MPS to bring MPS editors on the web. At least nothing that I'm aware of that there's actively something going on. I might be wrong, and somebody from JetBrains knows more. Yeah, but this is all I can say. The company where I'm working for is building something that tries to bring something like MPS on the web as well. But there's it's not open source, and it's also not publicly available at the moment. Ah, okay. So you used MPS to prototype it, and then you so you generated. So you used MPS to generate some web editor, or did you just use MPS to prototype your language and then build it with some other technology stack? Ah, I see. Yeah. Yeah, this is pretty fast in MPS. You can easily change the language and the meta model behind it, and then try out different things and explore the domain with the actual experts and show them how it would look like in the tool. Ah, okay. I see. Yeah, but at the moment I'm not aware of any efforts there. um okay. So but actually you can ask on there's a Slack instance for MPS here, which where a lot of JetBrains people are there as well, and quite a lot of other MPS users. So if you are interested in it, just join the Slack instance, and we also have a channel dedicated for the stream. So if you have input, ideas, or any critics, feedback to the streams here, just can also ping me there and leave feedback there as well, or discuss further ideas what we could do in this kind of format. Okay, so let's get back to the type system. We now have a pretty basic rule that only checks if there are duplicate variable names, but we also want to ensure, for instance, that we have types at all. So our program at the moment has no types at all. So if we go to a number literal here and we click the language debug context menu and we want to show the type, we get a notice that the currently selected node has no type. So you can either right click on any node in the program and then go into the language debug menu and select show type, or you can press Command Shift T or Control Shift T, depending if you're on Windows or the Mac. And yeah, we get the same message here, so that there is a node type associated with the number literal. So let's fix that first. So what we need to do for this is we need to define a rule how to calculate the type of a number literal. And to do this, we use inference rules in MPS. So we create a new inference rule for a number literal. And the type system of MPS is not, you don't implement the type system in an imperative way. So what you do in MPS in the type system is that you contribute equations to the overall type system, and then the type system tries to solve the equations that you have put into it. Sounds complicated at the beginning, but it's actually not. When you get used to it, it's no longer it's not that hard. It just needs to get some getting your it needs to you need to get your head around it in the first place. So what we want to do is we want to express that the type of our number literal. So the number literal that we get here as a parameter in this case is the node in the overall AST, and we want to associate the type and the type system with this node in the AST. So how we do that is that we use a type of operation, and then as a parameter to it, we use the number literals. So what we tell MPS here, the type of this number literal. What we want to tell MPS in this case is insert an equation to the type system that describes how the type of our number literal is calculated. Okay. So for a start, we can just say the type of our number literal is a new node, and then we just use an integer type. So integer type this. Okay. So what does this mean? So it means that in the equation, so this operator here tells MPS that this is an equation, or the type system runtime that this is an equation. So what we now told the type system in a declarative way is that the type of the number literal is equal to an integer type. And now this might seem strange at the first place, because we are instantiating an AST node here. So we are saying, so we would use the same concept to instantiate a new integer type. Also, if you want to put an integer somewhere in the AST, but the type system also operates on nodes, but it's the second. So they are not related. So this integer type that we create here will never end up in the actual AST that the user has entered. So this is only this integer type node here only exists in the type system at runtime. So let's build our language and take a look at the types again. So let's here and select our number literal. So what I did before is I pressed F5. So F5 tells MPS to re-evaluate the type system, rebind broken reference, etc. So it's like refresh the current indicator and apply the automatic fixes to it. In this case, I had to press it because there were no types associated with the number literal before. So MPS didn't know that when I was rebuilding the language, it needs to recalculate the type. So I manually triggered that by pressing F5. Every time you think there's something suspicious going on and you change something in your language and it's not reflected in the type system, press F5 and it will re-evaluate the type system for the complete editor that you are currently looking into. So if we now open the Type Explorer again, we can see that our number literal here has an integer type and that the other number literal here also has an integer type. And if we go to the string literal, it still has no type because we haven't defined any type system rule how to calculate the type of a string literal. So for all your expressions, you need to have they need rules how their types are calculated. And now we can go to the string literal and do the same as we did for the number literal. So we create a inference rule and we tell MPS that the type of our string literal is a new node string type. Okay. Let's rebuild this. Go back to our editor, press F5 here so that it so that it reevaluates. And now we can see that we have that the string literal is now of type string. The number literal is of type integer. We don't handle any cases at the moment, so if the user enters dot something, we don't support this yet, so we have no support for typing the number literal based on the value. We only support integers at the moment. But if we go to the plus expression here and we want to calculate its type, and we invoke the show type action here, it still tells us that there's no type associated with the plus expression. So we want to fix that. While for the literals, it was quite simple to calculate the type. For the plus expression, it might be a bit more complicated because the type of the plus depends on the operands. And so 10 plus 10, this is 2 integers. So the result of the plus operation is also an integer in this case. How can we express this in MPS? So let's go to our plus expression here and to the type system aspect. And to define the type, we also use an inference rule again. And first, so we want to do 2 things now. So we want to first tell MPS that the type of the plus is calculated through the 2 operands, but we also want to do something else. So what I want to forbid is that you can, for instance, add an integer to a string in this case. So what I want to ensure for as a first thing is that both of the operands in the type system, both of the operands of the plus, have the same type. How can we do this? So let's first start with the simple one, where we say the resulting type of the plus is based on one of its operands. So type of the plus expression is calculated by, and now we want to say the type of the plus expression is the same as the type of the plus expression, and then we can choose one of the 2 operands here. So let's just choose right in this place. Okay. So the resulting type of the plus is the same type as the type of the right side of the plus. And what happens now is we go back to our editor, to our small program here, and we go to one of these plus expressions and check for the type here. So we have this plus here on the left side, which has 2 integers. And since we calculate it currently only by looking at the right side of the plus, the type system has now solved the equation. So we have only declared how to get to the result, and now the type system has actually applied all the rules that we defined and came to the result that in this case the resulting type of the plus operation of the plus expression is an integer. And if we go to the one on the right, which has a string literal on the right side, we can see that the type system has solved the equations and came to the conclusion that the resulting type of the plus is a string. Okay, but now we want to make sure that in this case where the user has something like this, so where there's a number on the left and a string on the right, we would want to show him an error that this is something he is not allowed to enter. And to do this, we can also use the type system in MPS. So what we want to add as an equation to the overall type system is that the type of the plus expression left side should be equal to the type of the plus expression right side. So we tell the MPS that the type system is only valid in case where these types on the left and on the right of the plus are the same. So let's rebuild and go back to our program and press F5. Okay, and now we can see that there's an error marker here. MPS has added an error message here automatically and tells that the types here are not comparable, so it that the types are incompatible. So it tells us that well, let's open the type explorer, which also shows the error message, so it's easier to read. So here, the type explorer will also show at the bottom here all of the errors that the type system has put on the node where you invoke it on, and in this case, it's the string literal here. So it shows the type up here. And it tells us that there are incompatible types here, so it somehow tried to make sense of the equations that we put into it, but a string is not an int, so the equations cannot be solved, and you get this automatically generated error message here. Maybe we can provoke something. No, we can't. The model is too small. Okay, so we can also customize the error message. Right now, it's the normal generic one that you get from MPS. So it basically tells that that there is an error here, and that the types are incompatible. We could also customize the error message. So if you yeah, one thing. So right now, the error is here on the right side of the plus. So it highlights the string literal. But what we want to do is, what I would like to do is, I would like to have the error on the actual plus, because the problem is happening at the plus operation and not on the string literal here. So what we did here is that we inserted an equation to the type system that the type system should actually solve. But what we want to do is we want to only check this in this case. So we don't want to tell the type system the type of the right side is calculated while looking at the left side. So I know it gets a bit. So we don't want to have inference happening here. So we don't want to infer. So currently what we do here is that we insert an equation that the type system somehow tries to solve and to satisfy. And then at some point comes to the conclusion, this is a string, but it should be an integer. But what I want to do is I only want to check it. I don't want to contribute a checking an equation to the type system that changes the way how the types are calculated. So what we can do is we can go to this type of equals operation, and I hope there's no intention for it. Okay, but if we open the inspector on this equals operation here, then we can see that there is a field check only here. And if we set this to true, first of all, the editor changes, so it's now surrounded by the check here, so that's also visible directly when you look at the type system definition. But let's rebuild it. And now rerun it. Okay. Okay. Now the error is on the left side. So this is what I wanted to show here. So that depending on the path that the type system takes to your equation system, errors might show up at different locations. In our case, I can't really provoke MPS to So one thing you could encounter is that every time I press F5, the red arrow marker goes from the left to the right because the type system has chosen a different way through the overall declarative equation system. So what I would like to do is I would like to show the error message not on either side of the operands. I would like to undermark the whole or underline the whole plus here with a red error marker. So first of all, we only contribute a check here. And now there's also more stuff in the inspector down here. So there's the node to check, and currently it's set to auto. And node to check is the thing where if this check fails, so that the left and the right side have the same type, then currently MPS is automatically choosing where to attach the red error marker, and I would like to customize it. So I would like to say the node to check in this case is the complete plus expression. Let's rebuild and go back here. Okay, and now what happens is that we don't get the error on the left or the right side of this of the plus. The complete plus is underlined in this case, so it's more it's more obvious to the user where the error is in this case. We could also customize the error message in general that is shown. So the node to check here allows you to customize which node in the AST gets the error marker, but we can also provide a custom string here. Can either calculate it with an expression here, or we can have a static text like types of plus have to be both operands. Both operands have to have same type. Okay. We rebuild this and we go back to our workbook. You can now see that the automatically created error message is gone, and the error message that I have entered there is now shown to the user. So you can also customize what MPS shows there. The next thing we would need, or that we could do, is so currently we have a rule for the plus expression. The next thing we would need to do is we would need to define a rule for the minus expression. And for the minus expression, it pretty much looks the same as for the plus, right? So the type is calculated with one as the type of the minus expression is also calculated by one of its operand, and we want to ensure that the operands have the same type, so that that we can ensure that also for a minus this works as expected. So we can go here define the same type system rule, inference rule for the minus. I just copy and pasted it now. Okay. But then this. Now if we rebuild, get the same behavior for the minus as well. So 10 minus 10, that works. If we replace this with a string, get an error. And we would now have to do this for all of the other expressions as well. So not only for the minus, but also for the division and for the multiplication. And we also have a third expression, which is the equals expression. So this is the equals expression. And for this one, the type system looks a bit different. So if we compare two things, the result of the comparison is a Boolean, right? So it's either true or false. The resulting type of the equals expression is always a Boolean. So let's define that as well. Go to the equals expression type system. Add an inference rule here. And first of all, we want to define that the type of our equals expression is equal to new node Boolean type. Let's rebuild and go back to the and check the type of our comparison here of our equals expression. And now we can see that that the resulting type of the equals expression is a Boolean. I'm just going to add one more thing and then I have to stop for today because my voice is otherwise giving up again. So what I want to do as a last thing for today is that we do not only calculate the resulting type of the equals expression, but we also ensure that both of the operands are the same, and we can do this the same way we did in the other expressions here. So this as well. Remove the custom error message here. Rebuild. Okay. So now this completely and do 10 equals 10. This works because both of our operands have the same type. So it's an integer and an integer. And now let's replace one side with a string. This is also one thing I will still do today and change the alias there. So something like this. And now we get the error message that these types are not comparable, that these types are incompatible, so that we cannot compare an integer and a string in this case. Obviously, we could also allow this, but depending on the semantics of your language, this might or might not result into always false or not. But in our language, I would like to prevent this, so I can only compare things that have the same type. Or when we add more things later, we might go. We also will encounter cases where we want to use like subtyping, but more on that in a later episode. One thing I still want to do today is that it's currently quite ugly to enter string literals, right? So instead of just typing the normal quotes, you have to select string literal from the code completion menu here. So let's change that actually. This is super annoying. So to do this, we just go to the string literal. One thing I use heavily is Control N, which so if you have some experience with MPS, you might already know it. It allows you to search for a node, or a root node in this case, based on the name. And it's quite handy to go to concept definitions when you know the name. So in this case, I know that my concept is called string literal, so I press Control N, open the node chooser here, and then just select the string literal here. And it has no alias at the moment. This is why it shows up as with the concept name in the code completion menu, and I would like to bind it to the quotes character here. So I just change the alias, and now when you type the quotes, you automatically get a string literal, so it behaves a bit nicer. Okay, so I really have to stop now because my voice is almost giving up. Next time we will continue on the type system, so on Thursday. So I will keep to the regular schedule from now, except something goes wrong or I get sick again. But the current plan is to do the next episode on Thursday, 7 o'clock Europe time. So yeah, and in that episode we will take a look at the at some more advanced type system rules. So right now we have quite a lot of code duplication in our type system. So there is the rules for the plus, the rules for the minus, and for the equals. They look pretty much similar with minor differences. And MPS has some neat features to actually get rid of this duplication. And I will show you how to do this next time. Yeah, I will commit the code as usual. So you can find the code on GitHub here. I will commit it right after the stream and then push it to GitHub as well if you want to take a look at it on your own machine. Thanks, Mar. You can just download the code. There's also instructions on how to download the dependencies that the project has. So there's it uses the MPS extensions. There's a link to the exact version we are using. Yeah, and if you have any feedback, either leave it there on the GitHub repository, open an issue if you want to see something in the language that you are interested in, or see you on Slack and discuss there. So thanks for being here today. I hope you have a nice evening or day, depending on where you are. So yeah, that's it for today. Bye.